So miracles do happen, I suppose. Hey. Okay, so I asked you, offered you the ability to do a bonus problem. Boy, those colors look a lot better, don't they? Or they look different. Seems like you can make out the colors a little better. We'll see. I asked you to do the, anyone else have the bonus turn in? All right, there are a couple of loose ends we need to tie up with 11.8. I'm not going to do any more problems. I just want to point out some things that Lagrange multipliers, the concept can be extended out a little bit further. Everything we've done so far, we've had a function we're trying to optimize, which we call the objective function, and then we have a constraint. So like in the problem for bonus, you had shortest distance between a point and another point, and then you constrained it to the sphere. There are problems that you could do where you have multiple constraints. So let's say that you have a problem where it's like, let's find the shortest distance between that projector and a cylinder. Then you could find that cylinder would be the constraint, right? But what if you then said you have a cylinder and you cut the cylinder with a plane? Then you have like an ellipse, don't you? Then what you're doing is trying to find the shortest distance between that projector and that ellipse. Well, the plane is one constraint and the cylinder is another constraint. So now you have two constraints. So if you ever have two constraints, then instead of doing the gradient is equal to lambda gradient, gradient of f is equal to lambda gradient of g, you have to then say lambda gradient g plus mu gradient of h, where h is your second constraint. And then you have your two constraint equations, and what winds up happening is you have 5 equations and 5 unknowns. You have the gradient right here, partial of f with respect to x is equal to lambda, partial of g with respect to x. This is the new part right here, plus mu h with respect to x. Same thing with this one, this one. I'm not going to do any examples like that. Just know that it exists. The algebra, as you might imagine, gets a little more complicated, right? But it's all the same method. You set up the equations, you work through them. No, it's just on the g partial with x. All right. So in that code, remember I wrote all that code? I believe I do have one where I can put in both constraints, and it will work. I only say that because I offer this code to whoever would want it. If you ever planned on getting Mathematica, you could have it. All right, so now we're going to move in chapter 12. 2 more chapters to go. It's exciting, huh? We're halfway there in terms of chapters. So the title of this chapter is Multiple Integrals. So everything that we've done up to this point has pretty much been, well, how much integration have we done? We've done some integration when we were trying to go from like acceleration functions back to position functions. We did some integration, but other than that, everything has pretty much been derivatives, right? Partial derivatives. And so now chapter 12, we start to get into multiple integrals or multiple integration. So double integrals is the first thing we start with, and then we'll get to triple. Triple will be later on though. So double integrals. Remember that in Cal 1, there were this idea of Riemann sums. How many of you saw Riemann sums in Cal 1? Maybe you didn't need me to remind you what it was. Here's what a Riemann sum was. You're trying to estimate the area underneath the graph. So you have this blue curve, right? You're trying to estimate the area underneath it. So what we do is we put rectangles in there. And we say, let's add up each of these rectangles. And that area gives us an approximate area, right? And then the more rectangles you put in there, the closer and closer you get to the true area. And if you put an infinite number of rectangles in there, then that is the true area. So do y'all remember seeing this in Cal 1, Riemann sums? And depending on your instructor, you may have spent a lot of time and actually done Riemann sums by hand. Those are very tedious, but some instructors do that. And some of you were just shown like the idea, and then you went straight to the fundamental theorem of calculus. All right, so let's talk about this, why this method works. Because we need to understand this before we can do what we're going to do today. So what we did, and it's kind of weird, isn't it, looking? Huh. All right, so what we did was, when you're looking at one of these rectangles, you first look at the entire domain, which in this case, it looks like it goes from 0 to 5. And then you take one little rectangle and you try and come up with a formula that gives you the area of that rectangle. But you want that to be an arbitrary rectangle. You don't want it to be exactly fixed. You just imagine any rectangle in here has to have some form to it. So that's what this is about. We have a domain from A to B. In this problem, it was, what, 0 to 5? And then we take this little infinitesimally small width of a rectangle, which we refer to as delta x, or later on we refer to as dx. So dx is the width of that rectangle. The height of the rectangle is the function's value, right? Whatever the function is, that's how high you want to go up. So if we're back here, we take a rectangle over here, the width is dx, but the height is whatever that blue function value is. We go to a rectangle over here, the function value is different, so the height's different, right? So the height depends on the function. So if this is the formula for the, I don't know if y'all can see, this is area is approximately equal to the function's height here times dx. Length times width, or width times height would give you area. And if that's the formula for the area of one rectangle, then what we want to do is add up. So this is a sigma notation. You take the sum of all of those rectangles as you let n, the number of rectangles, go to infinity. And that's exactly what the integral symbol represents. Were y'all told that in Cal 1? This symbol, the integral symbol, this stretched out S, is representative of this right here, which is a sum, which is why it's an S. And then when you do the limit, as that sum goes to infinity, you get the actual true area, the true integral. All right? So important that we understand that if we ever want to add something up forever, we're going to have to integrate, right? And then what's in here is the formula for what we want to add up. In this case, width times height gave us our area. This is just a reproduction of the same thing. I don't know why it's there. So now what we're going to do is we're going to try and use the Riemann sums to find the volume do you want to, yeah. Hold on a second. All right. We want to look at a surface because we've been looking at surfaces in three-dimensional space. We want to look from that surface down to the XY plane and imagine finding the volume underneath it. So now we're three-dimensional instead of two-dimensional. So here's the idea. We have a function. Let me bring the function in here. Where is my function? Sorry, I'm not sure what my O here does. Can you all see the surface? Right? The yellow thing, yeah. Let me take some of these things out of here. Unfortunately, I can't take them all out. Okay, you can kind of see that surface, right? And we're trying to estimate the volume under that surface. So what we do is instead of taking rectangles, we take these rectangular boxes, right? These parallel piped things, right? And we find the volume of each of these, and we try and determine that if we add up all those volumes, right? Now, of course, the more that we take, in other words, the smaller the width and length of those little piped things, the more accurate it will be, right? you can see right here, the Riemann sum is 42.24, so it's calculating what it is. And this is the actual true volume underneath. It's 42.66666, whatever, forever. So we're getting close. If I go better, more rectangles in there, or more smaller parallelepipeds, then you can see I'm getting closer, right? And then let's see if I can do this without bringing my computer to its knees here. There. So you can see that's a pretty good estimate of the volume, 42.64, 42.66. So we would need even more to get to converge over to the true volume. With me? You see, it's the same idea as it was with Riemann sums, but now we're three-dimensional. So what we need to do is come up with a formula, right, that represents adding all those things up forever. Let me pull it back out to 5 and 5 so I don't slow everything down. Now that's the true volume right here. That's if you had infinitely many rectangles in there, it would just become a perfect solid, and it would match the curvature of the actual surface. So we're shooting for the volume of that thing. All right, so same idea that we had just now in Cal 1. We have a domain, right? So on the ground, let's imagine if you're looking from that solid, that surface down. Right now we're going to be looking at our domain being a square, or not a square, a rectangle on the ground. So we're going to take a rectangle on the ground and we're going to imagine looking up into the surface and trying to find that volume below, right? So what we do is we take our domain, our x values are between two constants, our y values are between two other constants. Then we take this infinitesimally small little rectangle in here. The width of it we will call delta x, the height of it is delta y, which will eventually turn into dx dy. So there's our little, in three-dimensional space, there's our delta x, there's our delta y, and then above it we have that rectangular parallelepiped. The height of that is exactly the function's value at this point, right? Now what do I mean by this point? What point? Because this is, I mean, there's a bunch of stuff in here, right? This yellow. So when I say the function's height there, you almost have to go back over here to this picture. When I said the height of this function, right? What point am I plugging into the function to get the height? Because isn't it different on the left side? Isn't the height over here different than the height on the right side? Isn't it? So what point am I picking? Do y'all remember in Cal 1 what they said about this? It can be any point, right? Why can it, not any point, like any point over here or over here, any point in that little dx. Because as it gets smaller, right, it actually starts to go to the same point. So it doesn't matter. So in this picture, right here, this picture, I don't know if you notice this, but if this is the rectangle, I'm actually taking the point in the middle to get the height. See that? In this rectangle, I'm taking the point in the middle to get the height. If I wanted to, I could take the point on the left instead. So here's my rectangle. I take the left height. The rectangle, I take the left height. Take the left height. See the difference? Or on this one, I could take the right height. So I go to my rectangle. I go up to the right side and take that height. And notice that when I do this, look at my estimated area. 6.81, or sorry, 6.18. There's the true area, 5.7. So I'm off by quite a bit, right? If I do the left side, 5.2, 5.7. So I'm still off. If I do the middle, it's pretty close. But it doesn't matter, because as I go to more and more rectangles, look, 5.75, if I do the left side, 5.68, right side, 5.81. So they're all getting closer and closer, regardless of the side. So picking that point does not matter. It can be any point in there. And that's the same with this. When I say f of x sub I, y sub I, I mean any point in that little yellow rectangle. Plug any point you want up into the surface, take that as your height, and it'll work, because as we get more and more rectangles, they smash down, right? And they get smaller and smaller. So the volume of this is length times width times height, right? This is the height, this is the width, this is the length, right? Either way, you could switch the order of these, couldn't you? But if that's the volume of that one rectangle, then all I need to do is add them up forever, right? So if we want to add things up, we have to do summations. Well, this summation would be a double sum. So what you do is you would go down like parallel to the x-axis and add them up, right? And then you'd move down the y a little bit and go down the parallel to the x-axis again, move a little bit, go down again, move a little, go down again, move a little, go down again. So this double sum, this first sum moves you down like parallel to the x-axis. The second sum will move you over and then down again and then over and down. Does that make sense? So like you're going back and forth down these rows, almost like you're mowing grass back and forth. That's the way you're doing. You're adding up all the volumes. So since it's a double sum, it becomes a double integral. So you have two integrals, and then the f of xy dx dy is the true volume underneath that solid, or underneath that surface. And then it reproduces. I don't know why it did twice. Also notice something here. This is going to give us the total volume over R, where R is a rectangle, right? So it's important for us to understand that this formula works when the bottom, right, is a rectangle. Yeah, because it's not always going to be a rectangle. So we're starting out with the easy case. So our limits of integration go from A to B and C to D. So here's that same note rewritten. The true volume, the volume between a surface and the xy plane, which is z equals 0 over a rectangle. Notice this notation. This notation we'll use for a rectangle in two-dimensional space. AB is your restriction on x, crossed with CD is your restriction on y. Then here it is. This is what it is. Now, what's the difference between these two? I'm saying double integral over the rectangle of the function dA. What is dA? What do you think that represents? dA. Derivative or differential of what? Area, because wasn't the area on the ground, that little yellow rectangle or rectangle on the ground, wasn't that dx dy? So that little yellow thing on the ground, the shadow on the ground, was a rectangle, and so it has area. So we're saying basically this is the height of the function times the infinitesimal area. Now, what is that infinitesimal area? It's dy dx, and then here's the function. Do y'all see that? Now, because this is multiplication, you could flip these, right? And you could have that instead. But notice what happens if you flip this. What happens to your integrals here? They flip. So on this one right here, notice that, I can't do that. Right there, I can't grab it. Okay. That right there, the y, right, this inner integral goes from c to d, and that's our restriction on y. And then the outer integral, or the outer variable x, is a to b. And then down here, we switch the order here, so these two switch. Yes? All right, so now, again, noticing the difference, the order of integration. If you have a double integral, what we'll do to integrate is we'll actually do this inside integral first. So that you can imagine there being a parentheses there. We integrate this. After we're done, we integrate again. But when you integrate this inside one, since y is the variable, right, in that integral, that inner one, since y is the variable, we treat x like a constant. So when we do our antiderivative, we treat x like a constant on this inner integral. Once we do that, we get our answer. And then on that answer, we treat x like the variable. Okay? If we do it the other way, if we do the x inside, then the first integral will be with respect to x, treating y like a constant. Then after we're done with that, then we treat y like a constant. So I'm going to be using this terminology of an inner integral and outer integral, the inner one, and then the outer one. So let's do an example. Find the volume underneath this thing on 0202. So here's a picture of what's happening. Right? There's our ground, that's 0202. I have a surface above it. Those colors do look pretty good, huh? And then here's what happens if I take all those points in the green and plug them into the function. I get this thing up here, right? That's just the green plugged in, and it creates that kind of square up on the top of the surface. And then what I can do is I can say, what's the volume below that? And I'll pull the surface out. That's it right there. So we're trying to find that volume. Understand? Okay. So here's what we're going to do. I'm going to start off by sketching the domain. So find volume under f of xy equals 16 minus x squared minus 2y squared on 0, 2, 0, 2. Now, sketching of the domain is something that will be valuable to us later. Right now, I mean, there's not a lot of thought to this, right? The domain, it's a square. So here's our domain. So this is our R. They use R for rectangle. I would like to know the double integral over R of f of xy dA. That's what I want, right? This represents the volume underneath F with respect to area. For us, this will be double integral. Now I can go dx or dy. Do you think it matters which one I do first? Should I do the inner one dx or the inner one dy? Or do you think it matters? It's not going to matter now. It will matter later. But when we're on a rectangle, it doesn't matter. That means when our domain is rectangular, the order of integration does not matter. And this is coming up later in today's notes. But for now, let's just say we're going to put the function in here. 16 minus x squared minus 2y squared. And then let's go dy dx. If I do dy dx, right, then my outer integral, the limits of integration would be what? The limits on x, right, which for us are 0, 2. Well, those are the same as on the y, right, so we can't get it wrong. But these 0, 2 comes from this one right here. And then the inner one will be the restrictions on y, which are these two. So I'll just say up here, these are restrictions on x, this is y. We good? I like that projector. It's hard for me to tell from the side, but it looks like you can actually distinguish those colors. Yeah, you can. Used to be that the red kind of looked like the black and the blue, and that's good. All right, well, here we go. So I'm going to do the inner integral, and I'm going to continue down here. So I'm going to say equals. The way I'm going to do this, I'm going to rewrite the outer integral, and put a bracket in here, and then I have my dx out here. So that's my outer integral, right? I'm going to do all my inner integral in here. So what we do when we integrate something is we use our techniques of integration. I want to integrate each of these three terms, but with respect to y. So I treat y like it's a variable. We treat everything else, including the x's, like they're numbers. So what is the antiderivative of 16 with respect to y? 16y. Okay. What is the antiderivative of negative x squared? Negative x squared y. Right? Because that's like a constant. So that may as well have said negative 10. Antiderivative of negative 10 would have been negative 10y. So antiderivative of negative x squared is negative x squared y. We good? Then antiderivative of negative 2y squared, negative 2/3 y cubed, right? My bracket needs to be moved out a little bit, sorry. Any questions? Now, what we normally did was we found the antiderivative, then we evaluated at the two endpoints, right? So our notation, we usually put this bar in here, right? Then we put the two places where we're going to evaluate. Which are those that we're going to evaluate? 0 and 2, right? But this is where we have to be careful. We have two variables in here, don't we? We integrated with respect to y. So we are going to be substituting 0 and 2 in for y, not for x. So I like to put here y equals 2, y equals 0. Again, that's useful later because we will be doing triple integrals, and you really want to know what's being plugged into what. You don't want to accidentally replace your x's with the y's and so on and so forth. So I'm going to now evaluate this. And to do that, I plug in 2 first, right? Then subtract from that what I get when I plug in 0 for y. So that'll be my next line. Integral 0 to 2. Bracket. Okay, here I like to write 2 sets of parentheses like this. Okay, let's plug in. So y is 2. We get 32 minus what? 2x squared minus 8/16. Now plug in 0 for y. Whole thing's 0, right? Let me clean this up. Integral 0 to 2. Let's get a common denominator. You got 32 minus 16/3 is 96 over 3 minus this, so 80/3 minus 2x squared dx. Can you sign in? I know I haven't been doing this, but just find today's date and just initial, please. I think I need to start doing it because, yeah, I should. All right, now what? You're in Cal 1 now, right? Just integrate this, get an answer. We'll go ahead and take this one all the way since it's our first example. 80x, or 80/3 x, and then minus 2/3 x cubed. And now we're going to evaluate this from, let's see, it was x this time, which we don't really need to put x, right? Because, I mean, the only variable here is x. But it won't hurt to get used to that idea. You plug in. You're only going to have the result when you plug in 2. So, what, 160/3 minus 8/16 again. All right. So what do we get? 144 thirds. And that goes in there how many times? 48. Is it 48? Someone check that. My brain like shuts off right around this point right here. Is that okay? All right. That's kind of weird that we get a nice number on that answer. I mean, you know what I'm saying? Like, it's really odd that that turned out to be a nice integer. But, hey, you know, it's what it is. That is the volume below that surface, or between that surface and the XY plane, over just that rectangle. So that's the volume of this. Cubic feet, yes. Uh-huh. Yeah, all of our volumes here would be our units cubed, but usually in math classes we usually don't assign actual dimensions to this because you go into some other class, you put the dimensions you need on it: meters, miles, feet, millimeters, and then just cube the unit. All right, let's look at the next example. Find the volume under y sine xy on this. X between 1 and 2, y between 0 and pi. And we'll come look at the picture in a second. Y sine xy. It was 1, 2, 0 pi. So I'll start with the picture. Ooh, man, those highlight colors come out nice too. Let me see what that looks like. Wow. That's a little dark though. Anyone else need to sign in? So I have everyone has been absent for all these days then, right? All right. So we want to find this double integral, right? Over this rectangle, which I'm calling R, I'll go label it R, of f of xy dA with respect to area. Does everyone, or does anyone have a question on this whole thing? Remember where I was saying like that's with respect to area and this is our function's height? Everyone's clear on that? I didn't lose anyone on that idea? Let me explain why I'm so concerned about you understanding that. Let me see. Because here's the formulas that I'll give you for just chapter 13. All right, I'm going to hand these out, just not yet. These are all integrals. This is an integral. I don't know if y'all can see that or not, but this is an integral over c d little s. So c represents will represent something to us. Like R right now is a rectangle on the ground, right? C will be something else. ds won't be with respect to area, it'll be respect to something else. That'll be arc length. And then later on, see, this integral c and dx is different than this one. And this one dy is different. And then here we have an integral. Oh no, that's still the same thing. ds, dy. Okay, so now we have integral c over c. Look at this, dr, but look at r. It's a vector. So it's with respect to something else. And then later on, you have where is it? Okay, here we go. C ds again. Okay, ds we saw. Here's d dA. This is the one I'm looking for. Here we go. D dA, right? S D capital S is different than D little s. And then we have S down here and then ds up there, but that's a vector. So what becomes very important to us as this class proceeds is understanding what all these things mean, because they represent something. Geometrically, physically, they mean something. And the way we come up with this formula depends on what we're trying to do. Here we're trying to find a volume, right? So it seemed natural to do length times width times height. Add them all up. Well, that's what we're doing here, right? Here we're adding up a bunch of dot products of some, what the hell's that and this, over S, which, well, this turns out to be flux, okay? So, I mean, later we get to that, but I want to make sure that everyone is clear with what this means to us now, all right? Because if you're just like, oh, I got the formula, I don't really, I understand what I have to do, and you lose sight of this stuff, then later on everything just seems jumbled up in a big mess. Does that kind of make sense to you? All right. All right, so now I'm going to convert this. So I can go, let's see, y sine xy. And I get to choose here, dx or dy first. Last time I did dy, right? Then dx. Well, that's to come, but we should. We're going to have to verify it, but yes. What's that?
I'll go the other way.
I bet you won't. Nope. Well, yeah, maybe you, this one will be, well, there's a moral to this story here because one way is easier than the other. That's the moral to the story here. Because let's just say we set it up this way. What would be the limits of integration on the outer one here? The outer one, 1 to 2. And then the inner one, 0 to pi. So we could do that, or we could have done this one. 0 to pi, 1 to 2. Same function inside, right? Just different order of integration. Let's talk about this. Yes. This one's easier? Yeah, if you do this one, the first time you integrate with respect to x, right? So you're treating y like a constant, y like a constant. So imagine that says 2 sine 2x, right? 2 sine 2x. Can you integrate 2 sine 2x? I hope so. Now over here, if you do it with respect to y, now x is the constant, and y is a variable here and here. So this would be like y sine 2y. How are you going to integrate that? Could you? Yes, integration by parts is what that would take. So that would be much more difficult. Well, not much more. It would just be more tedious, right? Understand the difference between the two? So I'm going to say, no, not today for this, and go for the other one. So this becomes integral 0 to pi, bracket. I want to do the antiderivative in there. I'll come back and do it. dy out here. So what would be the antiderivative of this with respect to x? Did you say negative? Negative cosine xy. That is correct. And you would go from 0 to pi. I'm expecting that you can go backwards and you can do this antiderivative from here to here. And if you're having trouble with that, all I'd recommend you do is, since you're treating y like a constant, just put a constant in there for y, and then figure out how would you do that. Like you would pull the 4 out first, right? Then you do the antiderivative of sine of 4x, which would be negative 1/4 cosine 4x, and then you put things together. And so either way, I expect that you could get from here to here. Now, I forgot to put something there, didn't I? I put 0 to pi. What's going from 0 to pi? X is going from 0 to pi. X, 1 to 2. Woo. Whoa. All right. X is the inner integral, so our limits were 1 to 2. Yes, but it canceled with the antiderivative of sine of xy, because you have to scale it by that same ratio. So, all right, now what? Plug in, what do you get? Integral 0 to pi. Plug in 2, negative cosine of 2y, right? And then minus would become plus cosine y dy. Do y'all agree? Now, antiderivative again, this time with respect to y. So what is the antiderivative of negative cosine 2y? Negative 1/2 sine 2y. And then the antiderivative of cosine y is just sine y. I'm evaluating here from y equals 0 to pi. Uh-oh. Uh-oh. Plug in pi. 2 pi, sine of 2 pi, 0. Sine of pi? Sine of pi is 0, right? So we get 0 when we plug in pi. When we plug in 0, what's sine of 0? 0. So sine of 0, 0, 0, 0. So the whole thing is what? 0. All right. What does that mean? We get 0 volume. So let's take a look at it. Here's our domain, right? 1 to 2 here on the x-axis, 0 to pi on the y-axis, right? That's what we got. We've got some surface, right? Whoa, look at that surface. See it? If I take just that rectangle's edges and plug it into this surface, and let me take the surface out, you can kind of see that some of it's above, right? And some of it's below. So if I look at the volume between the surface to the xy plane, I've got this volume up here, right? This volume up on the top is like a positive volume, and then the volume down here is like a negative volume, isn't it? And so the total volume are those two volumes added together, which are going to be 0. Just like when you were in Cal 1, if you had the integral from 0 to 2 pi of sine x dx, right, that would have been 0. Because even in Cal 2. Have I been saying Cal 1 all day? I meant Cal 2, right? Integration. It all bleeds together for me. So in Cal 2, you do all your integration. I apologize. In Cal 2, you're even shown, hopefully, that, for this you get 0. It makes sense because the area on top is considered positive and the area on the bottom is considered negative. And so they would cancel each other out. So the only way to really find the true area here was to do what? You would have to figure out where the x-intercept was and integrate from 0 to, in this case, pi. And then you go from pi to 2 pi and you change the sign. And so you wind up adding those two together and you get the true area instead of getting the 0, right? But the main point for me here, for you to understand, is that even the double integral is not going to be able to compensate for what's below the xy plane. So we have to be aware of that. If we get 0, that doesn't mean there's no volume. It just means that the volume up top cancels with the volume on the bottom. Now, we could have here found that x-intercept, right? And then broken our integral up into 2 separate integrals to find this area. Could we do the same here? Yeah, I would have to figure out where this surface does what? Touches the xy plane, right? So I'd have to figure out where the surface is equal to 0. And if we look at it from the top, come here, where the surface touches right? It's like along this ridge, right? And it looks like, is there more back here? I can't tell. No, that just tapers off right down in here. So we would need to figure out what this is. But what would be the problem with that? If I were to find that out right now, if I asked us to try and figure this out where this little ridge is, it would now break our double integral into two separate regions, right? Are they rectangles? They wouldn't be rectangles on the ground, would they? I mean, look at this one right here. It goes like this, and then it comes up like that, right? That's not a rectangle. And then the one here, that is not a rectangle. But we should still be able to figure something like that out, and that's where we're headed. What if your domain on the ground is not rectangular? Then can we find volumes? And we will, but right now we just have to concede that we could not find the total volume of this. We can find what the two together are, but not the total. Make sense? Okay, Fubini's theorem. So if f is continuous, so that means your surface is nice, doesn't have these weird asymptotes or anything happening. So if your function is continuous on a rectangle, then the order of integration does not matter. You can go either way. All right? Only over a rectangle. Verify it for this one. I'll do this one quickly. Quick. All right? xy squared, 0, 1, 1, 2. xy squared, 0, 1, 1, 2, dy dx, versus the integral, switch the order, 1, 2, 0, 1, xy squared, dx dy. These should yield the same exact results, shouldn't they, according to Fubini's theorem? Now, the way you would know that you could use the theorem is that xy squared is a very well-behaved function, right? It's never undefined. It's a polynomial, basically, and they act very nice for us. And then it's a rectangle. So antiderivative of this with respect to y is what? I'm doing the left one first. With respect to y first, 1/3 xy cubed, evaluated, y is 1, y is 2. Then dx. Plug in 2 for y, you get, what, 8/3 x minus 1/3 x dx. Am I going too fast, or are y'all okay with this? It's okay? 8/3 minus 1/3 is 7/3. So integral 0 to 1, 7/3 x dx is 7/6 x squared evaluated from 0 to 1, which just gives you 7/6. We should get 7/6 if we do it the other way. We'll see. So this integral over here was integral 1 to 2. And when we integrate the inside with respect to x this time, did we get 1/2 x squared y squared? Yes? Integrating this with respect to x this time, 1/2 x squared y squared. Evaluating x's from 0 to 1, dy. Oh, I like this one. If you plug in 1 for x, you just get 1/2 y squared. What happens when you plug in 0? 0, so we get that. Now plug in, find the antiderivative, sorry, you have to do that first. 1/6 y to the third evaluated from, let's see, y is 1 to y is 2. Plug in 2, 8/6 minus, now plug in 1, 1/6, which is 7/6. Same answer. As long as your function's well behaved, you're on a rectangle, switch the order, makes no difference. Well, well-behaved meaning they need to be continuous. Because if you have an asymptote, you could have some problems. Let's see. Next. Okay, this is a very special case of double integrals. It doesn't come up often, but when it does, you want to recognize it and possibly utilize it, because it can save you a lot of time. Well, not a lot of time, save you a little bit of time. And it's kind of useful. So let's say that you have a surface that it's a function of two variables, right? You have this surface. But when you look at it, you can look at it as a function of x times a function of y. So you can like separate them. For example, this one right here is like a function of x times a function of y, isn't it? X right here, that's by itself. The y here is by itself. They're separated by multiplication. This is not, because your x and y is trapped inside of a sign, right? So you cannot pull this apart as two complete functions, one with only x's, one with only y's. See the difference? If you have this, though, then when you do this double integral over your rectangle, you are allowed to rewrite that f as the x function and the y function separately. And then this is probably the only time in calculus that you can ever do this. You can take a product in an integral and split it into two integrals being multiplied. So what you do is you take the x function, you integrate that with respect to x using the endpoints of x, times the y function integrated over its endpoints. And it turns out to be the same, which is a good thing. So look, I'll show you this example. I could do that one. Well, let me show you this. The one we just did right here, we got 7/6. It was xy squared, right? Dy dx. It was 1 to 2. Is that right? 0 to. Wait a minute. 0, 1. I screwed that up. 0, 1 for x. 1 to 2. That's what we had, right? So I could look at this x here as being like my h of x, or g of x is what I used in my notes, g of x. And then I can look at this. That's probably going to block it out. It turned out okay. All right. This is my h of y. So I can split this up, two separate integrals, and multiply their answers. The first one will be the x function, so I use the limits here on x, times now the y function, which is 1 to 2 y squared dy. Y'all see that? Now the antiderivative of x is 1/2 x squared, evaluating 0 and 1, times over here 1/3 y cubed, evaluating 1 and 2. When I evaluate at 1 here, I get 1/2. When I evaluate 0 here, I get nothing. So times when I evaluate 2 here, I get, what, 8/3, and then I subtract what I get when I put 1 in here, so I get 1/3. 8/3 minus 1/3 is 7/3, and then times 1/2 is 7/6. Same answer. I'm sorry? Is what because it's area? It has more to do with the fact that if these can be separated like this, then when you do the antiderivative, let's say if we did this with respect to y, right? Then whatever this is going to be treated like a constant. And it's not going to have any effect on this. It's just going to come along for the ride when we do the first antiderivative. You see? And so whatever the antiderivative of this is, which is this right here, this is like the constant that got pulled out. I don't know if that makes sense, but it's because they're not interconnected. Yeah, and this one here, when we did our antiderivative here, see the x was in there, so that means we the y was in here. That's why we had to account for that with the antiderivative, so it didn't just come out by itself. I hope that makes sense. All right. There's another example in the notes here. I think I'm going to skip it. This one. You could break this up, though, couldn't you? And this is a function of x. This is a function of y. So you could split it up into two integrals and figure out what each one is. Here's the surface. You'd be finding the volume under that, which would be this. I won't do that one. Okay, some properties of double integrals, some things that we can't always assume are true, but here I'm telling you they are. If you have a double integral, you have two functions added or subtracted together. Of course, you can break it into two different double integrals, right? If you have a constant in front of a function inside of a double integral, the constant can come out. If you have a function is always bigger than another function, so you have a surface that's always on top of another surface over some rectangle, then the double integral should always be bigger than the double integral of f should be bigger than double integral of g. So the volume under the one that's on top should be more than the volume of the one that's on the bottom. Those all make sense? All right, I'm going to get to this one in a second. Let me remind you of something. In Cal 2, you start out with this idea of finding the area underneath the curve by just looking from the function all the way down to the ground, right? And that's where we came up with this idea of this rectangle. The height of the rectangle we said was f of x. The width was dx, right? Then later on in Cal 2, like right after that, you say, all right, now let's act like we have two functions. And maybe they hit each other at one point, and maybe at the other side they don't hit each other. And you want to find the area between those, right? So you again construct a rectangle. This time it only goes from here to here. And you add up all those. So when you look at that rectangle over here on the side, there's my x-axis. You want to know how high. Ooh, that's not very good. Let me try and match it up a little better. You had the blue curve up on top. You have the red curve on the bottom, right, like this. And you're trying to figure out what's the height of that rectangle. Well, you say the height of this is what? F, right? And you say the height of this one is G. Sorry, I didn't label these F and G. So the height here is actually your F, take away your G, right? So the area under this, the whole thing, the area under this whole thing, turns out to be the integral from a to b, and it was f of x minus g of x dx. That sound familiar? That formula right there that represents the area between those two curves comes from that idea. We have the exact same thing here, right? If you want to find the volume of the solid between two surfaces, you're going to have to take the top surface and subtract the bottom surface, right? This will be a very tough picture to draw, but I'll do my best. Let's say we have this. Let's say we have a surface on top, right? Let's say we have a surface below it, and we want to find the volume. sorry, volume between them, right? And then on the ground is the rectangle on the ground, all right, like this. Do y'all see that? That's R on the ground. Terrible picture, but I'm trying to do this real quick. So we have the ground, we have our volume between the two surfaces. Let's say that the top surface here is f of xy. Let's say the bottom surface here is g of xy. Then if I want to go in here and I want to create this parallel pipe in there, right? Bring that out here and take a look at it. Then on the ground down here, right? Then the width of it, right? dx, dy, same. But the height is actually what? From there to there is f. From here to here is g. So from here to here, again, would be f minus g. Same exact concept extended out into three-dimensional space instead of 2D, right? No? That's what this note says. Got two functions on a rectangle. It's always going to be your top function f. Here's your bottom function g. Here's your rectangle. That volume will just be that right here. That it? Is that the end of this section? It is. So, let me see where we are on our calendar real quick. We have no class when? Next, not this week, next week. Okay. Are there any questions on this? We're not done for the day, but are y'all okay on rectangles? You think seems okay, straightforward? This is just for rectangles. Yep. Of what? Sure. Yeah, that's a good idea. Why don't we do this? Find volume between f of x, y equals 16 minus x squared minus y squared, and g of xy equals x squared plus y squared on -1, 1 crossed -2, 2. Got it? So let's start with the domain. -1, 2, -2. Crap, hold on. Now this should work. What do these look like? Remember, this first one, the F one up here, is really like z equals 16 minus x squared minus y squared. And this one is really like z equals x squared plus y squared. Okay, pretty close. Cylinder would be if this was a constant. Like if this was x squared plus y squared equals 4, it'd be a cylinder radius 2. Because it's z, so we're going back all the way to chapter 10, where we're looking at quadratic surfaces, right? So what would you do if you would have a couple options here, right? You could look these up. Wait, was it chapter 10.6? 10.6, page 574. There was a table from that section. What they look like? Because one of these is on top and one of them's on bottom, and you need to figure out which one it is. Do what? Oh, you mean like doing them separately? Um, you could do it that way, but there's the danger that what if one of them? Let me see. Yeah, but we're not there. We're not going to do that yet. That's where we're going. The reason I'm trying to get us to look at it is because of where we're going with this. Is because the question that I would have later, not right now, would be find the volume between those, and I don't give you a rectangle, which means you have to figure out where they hit each other. So that would become a little bit more of an issue. So I just want us to start thinking this way. Like, what is this? So what is 16 minus x squared minus y squared? Parabola opens which way? It opens down. So let me try and see if I can kind of do a little graph of this. Look at this one right here. Let's just plug in some points. What would happen if I plug 0, 0 into this? What would I get? X is 0, y is 0. What would I get? 16. I'd be way up here at 16, wouldn't I? On the z-axis at 0, 0. What if I plugged in x is 4 and y is 0? I did that on purpose. I have 4 squared is 16, right? Y is 0, so I would get 0. So if my x is 4, this is my x-axis, this is my y-axis, this is my z-axis. What if I plug in y is 4 and x is 0? I get this, right? Where does this thing hit the ground? What does it look like if where this thing hits the ground? You set z equal to 0, right? That would be where this hits the ground. Let z be 0. What type of equation is this? Circle, right? Move your negative x squared minus y squared to the other side. You get x squared plus y squared equals 16. So you have a radius 4 circle on the ground. So it looks like this. It comes around the back side, right? Does this. And then I really don't like that. There. Okay, so it's like a paraboloid. Got it? Paraboloid, like this. Then, what's x squared plus y squared? What is that? So plug in some points. 0, 0. That would put you here, wouldn't it? The origin. Let's plug in something else. What if x is 0? What's y look like? And then let y change. What does z do? It looks like if x is 0, it's a parabola, right? Agreed? And then if y is 0, it's a parabola. So it's a parabola in both directions like that. But this time it's going up, isn't it? Instead of coming down. So it goes like this, like that. Agreed? Something like that? Now, like I said, later what we're going to say is, what's the volume between these? I'm not going to say over a rectangle, because they actually hit each other, right? And they enclose a solid. Like there's a ring where they hit each other right in here. And you can figure out what that is, and then you can find the volume between them. But the problem with that is then you're not on top of a rectangle. But we'll get to that. So which one is on top? Let's at least determine that now. Which is our top function, which is the one on the bottom? The top one is the 16 minus x squared minus y squared. The bottom one is x squared plus y squared. So this is like the f function. This is like the g. So my integral would be double integral over r. I take the 16 minus x squared minus y squared. I subtract from that the other one, x squared plus y squared. And then d, does it matter the order here? Order of integration? No. So dy dx. And my x's went from -1 to 1. My y's went from -2 to 2. That's it. I'm not going to go through it, but that's the setup. I would collect things together, right? This would be like 16 minus 2x squared minus 2y squared, then do your integration. All right, we're going to start 12.2. I don't know how far we'll get. So double integrals over general regions. So now we're going to move away from the rectangle on the ground. So this is what we have so far, right? We have this drawing of our region on the ground. We have the idea f and g, right? We can find the volume between those. That's what we just did. But now we're going to look at two new types of regions called type 1 and type 2. Type 1 and 2, these will cover a majority of the types of things we could see, type 1 and 2, but it does not cover everything. A type 1 region looks like this. Your x is between two constants, just like it was before, but now your y values are stuck between two functions of x. So as a picture, here's what it is. Notice that in this yellow region, if I draw a line from a straight line from that blue function down here, all my x's in here are always stuck between a and b, right? Every x value in this yellow is stuck between these two constants. But every y value in this yellow is always stuck between the blue and the red functions, right? You all see what I'm saying? Okay, so because of that, we have this type of a region. Y is between two functions, x is between two constants. Why couldn't you look at it the other way and go like this? I mean, if you do it that way, is everything in the yellow stuck between two constants? No? I mean, there is some number it's stuck between here, right, and here, up here. Yes? But look at it. Is your x between two functions? It's between the blue one and what? Whatever this line is. But what about if I move over right in here? What's wrong with this? It's stuck between what? The same function. So you could not figure out what that distance is, because it's the same thing on this side and this side. Does that make sense or not? All right, so when we have a type 1 region, when we can look at it this way, then your integral, double integral over, now notice we're using d. D is the notation we use for just a common region, instead of r, which we reserve for rectangle. The double integral over d of the function with respect to area will be integral from a to b, then g1 of x to g2 of x of the function dy dx. And that order cannot change. You are stuck, forced to do it that way. All right? So these two limits of integration are no longer constant necessarily. They are functions. These two are going to be constants. So if we actually are given a surface F and a surface G, and we want to find the volume between them, but this time on top of a type 1 region. Do y'all see that type 1 region on the ground there? We have our x's are stuck between a and b. Our y's are stuck between two functions of x. Yes? Then it's the same setup, except we subtract the two. So we did that in the previous section. I'm just reminding you that it would be the same. We can use the same principles as we did the previous section. So let's do this one. Find the volume under z equals x plus 2y on the region bounded by y equals 2x squared and y equals 1 plus x squared. And what I'll do is we'll look at that in a second. Let's actually act like we had nothing to look at and see what we would have done. So we want to find the volume under z equals x plus 2y on the region bounded by y equals 2x squared, y equals 1 plus x squared. So like we did in the previous section, 12.1, I always started by drawing the region on the ground, right? Which was a rectangle, which didn't really matter too much, did it? It's pretty easy to draw. This time, the region's going to take a little work. So we're going to go back, draw our x, y. And now you need to know what those two things look like. So y equals 2x squared is a parabola that opens up. And it's been changed a little bit with that 2 in front, right? So it's going to go like this. That's y equals 2x squared. Now, 1 plus x squared is another parabola that opens up, but this time it's been moved up 1. And it doesn't open as steep as the other one, does it? Right? It doesn't open as steep because it's just x squared instead of 2x squared. So I move it up 1, and it goes to the right like that, to the left like that, right? We've got something that looks like that. Now, you've got to know what that looks like. If you don't know what it looks like, you need, break out your, I don't know, old college algebra notes or whatever it is and take a look back at some of these basic functions. Or you break out your graphing calculator, whatever it takes to draw that region. So let me zoom in on this region. Is that a type 1 region? Well, if it's type 1, I should be able to draw an arrow vertically, or this little line segment vertically, and I should be able to do that everywhere in this region. And when I draw these little arrows, my x values always have to be stuck between two constants, and my y values always have to be stuck between two functions. And it's got to be the same two functions. So if as I draw these, are my y's stuck between the same two functions the whole time? Yes, between the blue one and the green one. And then my x's are always stuck between some point over here, right? And some point over here. which I'm going to need to figure out, right? So this is type 1. My x's and y's are bounded. What are my x's between? What are my y's between? Can you tell me what the y's are always between? I think that's easier than the x's right now. Just, you could tell by looking. Which one of these is on top? The 1 plus x squared, right? So 1 plus x squared, right? That's my bound on my upper bound on y. My lower bound on y is which one? 2x squared. Okay, now let's figure out what these 2 points are. So how do you find those? Set them equal to each other, the 2 curves, right? Because that's their intersection point. So to find this, the intersection of my 2 curves, so I set 2x squared equal to x squared plus 1. Subtracting x squared, get x squared equals 1. It happens at where? Negative 1 and positive 1? Right? Maybe you could tell by looking, but that's the way you would do it algebraically. So I know that my x is between negative 1 and 1. So I have my limits of integration for my double integral, don't I? And now I just need to figure out what the integrand is. What's the thing? What's the f of x, y? So what am I trying to find the volume under? This right here, right? Z equals x plus 2y. That is actually our f of x, y. That's going to go in the integrand. So help me out. I'm going to set this whole thing up. I'm going to go from where to where on the first integral? Negative 1 to 1. On the second integral, it's going to be a function. That's okay. 2x squared up to 1 plus x squared. And then my integrand, x plus 2y. And then order of integration here, dy dx. And you cannot change this, okay? You cannot change this. It's not a rectangle. Oh, well, on type 1 regions, yes. Type 2 regions can be the other way. 2 constants, and your x is going to be between 2 functions of y. All right, but we need to practice this integration. So let's see how this works. Because this is a little different, as you're about to see. It's not crazy, but it's just different. So what I'll do first, I'll write my outer integrand like this, brackets. I'll come in here, dx. So what is the antiderivative of x with respect to y? xy plus, what's the antiderivative of 2y with respect to y? Y squared. I'm evaluating this from y equals 2x squared up to y equals 1 plus x, right? Because I integrated with respect to y first, so that's what's going to be replaced. And the 2 limits of integration are actually functions. Now I'm going to go in here and replace all my y's with 1 plus x squared, and then after that subtract what I get when I plug in 2x squared for all my y's. And it's going to be a polynomial disaster, but it's going to be doable. So let me first plug in 1 plus x squared. Get x times 1 plus x squared plus 1 plus x squared squared. So that's what I get when I plug in 1 plus x squared into this for y. Then minus. Now I plug in 2x squared for y. So x times 2x squared plus 2x squared squared. And then all that crap needs to be integrated. Right? But this is just polynomial, right? You could distribute the x through, you could expand that out, you could multiply this out, you collect all your like terms, and then it's just, straightforward integration. Plug in -1 and 1, and you are done. So just dot, dot, dot after this. Okay, I'm not going to do the rest of that. Make sense, though? Now, usually someone will ask, or some student will be sitting there thinking this, but look back at this region that we're integrating over right here. And I'll have a student that will ask, well, wait a minute, could we not have just looked here? Boy, that was terrible. That's why I don't use a mouse to try and draw. Can't we just look right in here, right? Can't we just look right there and go, you know, that would change this, so it would go like, our x's would now be between what? 0 and 1 instead, right? And then the two upper and lower functions, right, the top and bottom would still be the same, but could we do that and double our answer? Well, the region is symmetric, isn't it? So could you? What do you think? What's that? Is it in this case? What are we getting? What does this double integral represent? That's right. You're going up to a surface and you're trying to find the volume below that surface, right? The fact that the region on the ground is symmetric doesn't tell you anything about what's happening above it. What is above it would also have to be symmetric in order for that to work. You may not be. And in this particular case, you are not. So here it is. Here's the region on the ground, right? That's the best I could do to get the region on the ground. No, it looks weird, but that's the region on the ground. Here's the surface. The surface is a plane. See, it's not symmetric. If I look at it from the top, right? Even though my region on the bottom is symmetric, how high this part of the plane is different than how high it is on this side, isn't it? So since we don't have that symmetry, I'll tilt it so you can see it this way. See? Probably be better. There we go. Come around. Yeah, you can kind of see it from there. And then, of course, if I just bring the damn solid in, you'll know exactly what I'm talking about. And take the surface out of here. Whoa. There we go. See that? So on one side, it's different than the other. Can you all make that out from the picture? So you could not change that integral from 0 to 1 and double the answer. It would be off. So that's what we're looking for, though. It's that solid. So it's a plane, everything below that plane, but above that region. That's pretty cool, yeah? This is the same sort of problem, right? Find the volume under this surface on the region bounded by 2x and x squared. So save us some of the trouble here. I'm just going to go through it. I'm hoping everyone could graph 2x and x squared, right? Parabola and a line. So our integral, this region right here is type 1, isn't it? Top and bottom, you draw a line through here. It's always the line on top, the parabola on the bottom. What's our restriction on x? Between 0 and 2. So our x's are between 0 and 2. Our y's are between, let's see, the bottom would be x squared, the top would be 2x. We would go double integral, right? 0 to 2, x squared to 2x, and then this would be our integrand right there. There's a picture. Yeah, dy dx. There's the picture of what it would be. Okay? That volume. I'll just put it down here in case you do refer back to these notes ever. And for that example, it would be integral, we said 0 to 2, right? X squared to 2x, x squared plus y squared, dy dx. That's what that one would be. I think this is a good place to stop. Type 2 is next, and we can knock type 2 out pretty quick. If you understand type 1, type 2 is pretty natural. Just everything changes, you know, now everything's a function of y instead of x. Now, homework-wise, let me see. I didn't give you any homework for 12.1? It wasn't on there? No? So let me tell you what you should take a look at. Most likely, your final's the next test, right? I can guarantee you there won't be a double integral over a rectangle on the final. I mean, that's a guarantee. It's never happened, never will happen, right? Those integrals are way too simple because it's just plugging numbers in. But you might want to just practice a little bit. So for 12.1, page, you got to start somewhere, right? So calculate the integrated. Some of this, the practice is in the actual integration. Oh, I'm doing the freaking problem, stupid ass. Okay, I like number 16. It was a long weekend, man. So. On these, just actually try and compute those by hand. All right, you'll get the practice with the antiderivatives, and then let's see, 31, 35. For 12.2. Page 707. This will be type 1. Yeah, I'm going to make them just type 1s. Again, this is just to kind of practice the evaluation. 3, 8, 11, 12. Let's just go 12. That's good. I have not graded the other bonuses, and I plan on giving you a handout for your next take-home quiz next class. I think now we have enough stuff. You've got Lagrange. We'll have some double integrals. I can actually give you something that has some substance to it. So just next class, I'll give that to you. All right. You have a good day.